In this tutorial video we will learn about Grover Adaptive Search and QUBOs in Blueqat. We will be doing this in Google Colab. Like we did in previous video, we will start with installation of Blueqat. We can do it by using this code !pip install Blueqat. Type the code that was shown earlier in Google Colab. Then click on play button and Blueqat will be installed. In this tutorial, we shall use a general version of Grover's algorithm and quantum amplitude amplification to provide a quantum algorithm for a general QUBO problem. Note that this is a complicated alternative to the QAOA algorithms using gate model quantum computing. It is known that adiabatic quantum computing is equivalent to gate model quantum computing. An important paper of Roland and Cerf proved that the speedup of O^n, obtained via Grover search on an entire solution space of size n, is exactly the speedup of the QAOA algorithms. In short, gate-based algorithms are theoretically equivalent to QAOA, but require coherent circuits with large number of qubits to set up and might not be practical to implement on a quantum computer in the near future. A quadratic unconstrained binary optimization problem, in its most generality, asks to minimize where Q is an n times n positive semi-definite matrix, R is a 1 times n row vector, X is an n-dimensional, 0, 1, column vector. Note: a constrained quadratic optimization problem has additional constraints on the vectors X. It is well known that as long as these constraints are linear, such a problem can be reduced to a QUBO. Solving QUBO problems fast is a very important problem in modern computing. This is because several optimization problems such as max cut, graph coloring, vertex cover etc. are QUBOs, as we've discussed in the earlier tutorials of this section. In this tutorial, we shall be implementing Guilliam-Warner-Gonchouia's algorithm for n equals 3. But, before we discuss GAS, let us recall the basic idea behind Grover search. Grover search requires the following components: an operator A that maps vertical bar 0 wrangle underscore n to the uniform superposition state vertical bar phi wrangle equals 1 fraction square root 2 caret n sigma I vertical bar I wrangle underscore n. In fact, A equals h caret O times n. An oracle O that marks states subset 0, 2 caret n1, so that the diffusion operator D that flips the sign of the state vertical bar 0 wrangle underscore n. The Grover operator is G equals eta caret dagger O, which, when applied left floor pi by 4 square root fraction, 2 caret n, I right floor times on a vertical bar 0 wrangle n, gives us a quantum state whose measurement is one of the entries of I with high probability. The components required for implementing GAS are an operator I such that an oracle OY such that f x to real number set, lambda greater than 1, num underscore iter, set to 3 by default. Uniformly sample x1 element of x and set y1 equals function of x1, set k equals 1 and I equals 1, while true, select Ri element of 0, selling bracket k1 selling bracket, uniformly at random apply Grover search with Ri iterations, using oracles A y I and O let the outputs be x, y. If y is less than yi, then set xi plus 1 equals x, yi plus 1 equals y, reset k equals 1. Else set xi plus 1 equals xi, yi plus 1 equals yi, k equals lambda k. I++, if the value of xi doesn't change for num underscore iter iterations, break. Let us consider the following QUBO problem. Q equals begin, P matrix, 1 and 0.5 0.5 and 2 end, P matrix, R equals begin, P matrix, 0 and -3 end, P matrix. Then we are trying to minimize. The major difficulty in implementing our program is to construct a quantum circuit for the operators A, Y and O. We shall use 2 registers. A key register with n equals 2 qubits corresponding to each variable in the problem, and a value register with m equals 2 qubits to store the different values of f, x0, x1, where the first qubit corresponds to the sign and the second qubit corresponds to the value. For general QUBO problems, m needs to be large enough so that max limits, x element of 0, 1, n, function of x, less than 2 m1. In our case, m equals 2 will suffice. This can be implemented using controlled phase operations. We first create the uniform superposition state. For a fixed y, ay needs to evaluate function of x, y, which we will achieve by encoding y into the value register first, via phase gates with angles fraction of pi y by 2, and pi y. For the term x0, we put controlled phase gates of angles fraction of pi by 2, and pi on the first and second qubits of the value register. For the term x1, these angles will be fraction of pi by 2, and pi. For the term x0 by 1, we need 2 multi-controlled phase gates. In general, for a term ax, I1, x, I2, c.x, ik, in the polynomial, we put phase gates with controls on the I1, ik th qubits and angles fraction of 2 pi, 2 m, 2 j on the jth value register qubit. Finally, after these controlled phase operations, we apply an inverse QFT to the value registers to compute vertical function of x, y wrangle on the value register. Below is a circuit implementation for AY. We can reduce this circuit further to rewrite it in terms of 2 qubit gates. As 2 controlled phase operations can be decomposed into C-phase and CNOT gates, we obtain the following circuit. We now implement this on Blueqat. Recall the QFT circuit from our tutorials. As the oracle O needs to flip the sign of the states which have 1 in the first value register qubit signifying a negative sign, we only need to apply a Z-gate to implement this oracle. We need to implement the reflection around vertical bar 0000 wrangle on Blueqat SDK. This can be achieved via the following circuit with an extra on-Kila qubit. Now we solve the optimization problem of minimizing function of x0, x1, equals x0 plus x0 by 1 x1 on the Blueqat simulator. That's all for today. Thank you.